So a quick review of conservation of energy. When we talk about conservation of energy, we're usually saying energy before is equal to energy after, which would mean that kind of like E1 equals E2, or I suppose you could also say EI is equal to EF. So, although the amount of kinetic or potential energy that an object has may change, its total mechanical energy will always remain constant. Now, what I want to add to this is something that you will need for the next assignment that you're going to work on. And so if we were to take a look at this set of equations here, we would say mgh1 plus 1/2 mv1 squared is equal to mgh2 plus 1/2 mv2 squared. Now, let's say I give you all of the information. So we know the mass of the object. We know it's on Earth, or near the Earth, so g is 9.81. We know its initial height. We know its initial velocity. So I've got this, got this, got this. Know the mass. I know that for each of these. I know the initial velocity. There it is. We're still on Earth. Height is still known. And what we're looking for is V2. Algebraically, how do I solve for that? And there's a couple different ways you can do this question. But if I were to ask you to solve just algebraically for V2, the question is, what do you have to do? So let's take a look, getting rid of the arrows, at what we would do algebraically. So the first thing is we want to get the term that has V2 by itself. That means I'm going to subtract mgh2 from both sides. Right, and so now what do I have? Well, I have mgh1 plus 1/2 mv1 squared minus mgh2 is equal to 1/2 mv2 squared. I want to get the v2 by itself now. I need to multiply both sides by 2 to get rid of the 1/2 and divide both sides by m to get rid of the m. So let's do that. Divide this side by 2, divide this side by m, multiply the whole side by 2, divide everything by m. Right, so mathematically, I'm now left with v2 squared is equal to. Now, a couple things we got to look at here. Notice that each term here has m in it, and it's the same. That means I can get rid of this m because each of them can be divided by m. But the 2, I have to use the distributive property, multiply that through. So I have 2gh1 plus 2 times 1/2 is just 1. So v1 squared minus 2 times gh2 is equal to v squared. And now if I want it to just be v squared, I need to take the square root of both sides. And so my final answer is going to involve me square rooting both of them. And so my final answer is going to be that v2 is equal to, let's make it look like a v and not whatever that handwritten thing is, the square root of 2gh1 plus v1 squared minus 2gh2. Right? You'll need something like that, not quite as complicated, for one of the assignments coming up. Moving along. You can check this in your book. This is, I believe, page P19. I separated here into 2 pages, but it is all in 1 page on P18. So at total mechanical energy here, at the following positions. At A, all of its energy, assuming that's the top, is potential energy. B, all of it is EK. C, assuming again that it's the same height as A, which it should be, it's all potential energy. All right, where does the pendulum have maximum speed? It has its maximum speed at B. Minimum speed, A or C. Greatest potential energy, A or C. Least potential energy, B. Greatest kinetic energy, B. Least kinetic energy, A or C. All right. Pendulum has a mass of 1 kilogram, rises to a vertical height of 0.320 meters. What is the maximum gravitational potential energy of this pendulum? EP equals mgh. EP then equals mass of 1.00 kilograms times 9.81 times a height of 0.320 meters. And we plug that all into our calculator, and we end up with our final answer of 3.1392. So 3.14 would be how we would round in terms of joules. Right. Now, second part, if the pendulum is released, what is the maximum kinetic energy? Well, if it has 3.14 joules of potential energy, the most kinetic energy it can have is the same 3.14, assuming all that gets converted. What's the maximum speed then? Well, in this case, I take this kinetic energy and figure out what speed is it moving when it has that kinetic energy. So again, mass was 1 kilogram. We know EK is equal to 3.14 joules, and we want to solve for V. So EK equals 1/2 mv squared, which means that I multiply both sides by 2, divide both sides by m to get V by itself, and then square root. So 2 EK over m, all square rooted, is equal to V. And I plug that into my calculator. End up with 2.51 meters per second. Again, my calculator spits out 2.505. Right, so that's so you can check your answers in the book. Quickly moving ahead. Thermodynamics, 2 laws that we care about. The first law of thermodynamics is basically saying energy is not created or destroyed, only changed from one form to another. Second law is more complicated. It says that heat flows naturally from a hot object to a cold object, but never from a cold object to a hot object. Practically speaking, what does this mean? It means that in any energy conversion, energy will be lost to its surroundings, or that all energy transformations are inefficient. As in, there is no such thing as a 100% efficient energy transformation. We always have energy lost to someplace we don't want it going. And between these two things, really this helps us explain and understand why there is no such thing as a perpetual motion machine. Because we can't have something turning energy or creating energy forever without any extra input energy. Because energy is not created by a machine, and in any machine, energy will be lost to the surroundings. Because of these, the system is inefficient. And again, if we put more energy into a system than we actually get out of it, we say it's inefficient. Every energy transformation involves input and output energy. There will always be more input energy than useful output energy. And the ratio of useful output to input energy is known as efficiency. This is a formula that you need to memorize. Useful output divided by total input times 100% gives us efficiency. They both need to have the same units, so they can both be kilojoules, they can both be joules, but they both need to have the same units. And that takes us to the end. Now, a little trick that you can use here is that useful output is always going to be smaller than total input. So once you know your 2 types of energy, it's going to be smaller number divided by bigger number. Multiply by 100%, and away we go. Thanks.